Okay, so hi everybody. Uh, in this video, I want to talk a little bit more about the nuclear transformations we talked about last time. We talked about things like alpha decay and beta decay, and how these are ways where energy that is tied up in mass can be converted into other forms. And we saw the basic ways this can happen. And in this video, what I want to talk about is under what conditions and at what times these sorts of transformations can occur. We talked in the previous video that transformations can occur spontaneously when they result in a reduction in mass, which releases energy. But now we have to understand when those transformations occur, because this is relevant for understanding just how these processes work, and also for whether we can actually efficiently extract that energy for other purposes. And there's going to be two different types of phenomena we're going to focus on today. One are the kind of transitions we've already talked about, which are things that happen spontaneously at predictable rates. And the other are things that can happen that are a different kind of process that only occur under specific conditions. That is, they depend on what the environment the nuclei is in. So that's kind of the goal here today. So let's first focus on these changes that are regular and predictable. These are, again, the various types of transformations we talked about, the production of alpha particles, beta particles, and gamma rays. These processes are often called nuclear decays. So sometimes this is called alpha decay, beta decay, and gamma decay. Each one of these processes seems to be basically determined by the internal structure of the nucleus. The rate at which this happens doesn't depend on the environment at all. It doesn't matter if these nuclei are in something deep beneath the Earth, up in the atmosphere, or in space. They happen at the same rates, as far as we can tell. And to some extent, that makes sense because nuclei are buried deep into the core of atoms. It's hard for things outside of the atom to affect these sorts of processes. So these being kind of things that are internal to the nucleus mean that they kind of behave the same under most conditions. But an important thing to understand is, in spite of that, it is not the case that all of these transitions take the same time to occur. That is, if you have a nucleus that would naturally split apart due to alpha decay, these sorts of nuclei don't just last some particular length of time and then transform. If you have something that undergoes beta decay, like carbon-14, a single atom of carbon-14 does not last a fixed amount of time before it decays. Some of them last short periods of time, some last longer. The rate at which they transform is defined instead in terms of a couple of parameters. It's actually just one parameter, but can be written down a couple different ways. These parameters are called the decay constant and the one you're probably more familiar with, the half-life. So the decay constant is kind of the easier one to measure experimentally. What the decay constant is it basically tells you what fraction of the material transforms in a fixed amount of time. So for example, if you have something with a decay constant of 0.1 per year, then if you had a pure sample of this material that is prone to decay in a particular way, 10% of it will decay within a year. If you have something instead with a decay constant of 0.01 per year, just 1% will decay within a year. Now, this is a number you can measure. You can collect a bunch of nuclei and see how many have decayed in some reasonable amount of time. For some materials, they decay very quickly, so this might be just days. For some of them, it's quite slow, and so you'd only see a small fraction decay in a short period of time. But what's a thing to notice here is I'm not telling you anything else other than how the material was they're together at some point. I don't know if this material was thousands of years old when I got it, or was just made yesterday in some sort of nuclear reactor. It doesn't matter. It doesn't matter if it's in the form of a particular oxide or a solid or a gas. It just means that 10% of it transforms in a year, or 1%, depending on the material. That's a bit odd. It indicates that there's something fundamental about this time constant. And I want you to keep that in your mind. Now, this is one way to explain how the amount of material changes over time, but it's kind of a snapshot. The other way that we describe how this material decays is in terms of this quantity known as a half-life, which have creeped into, fair amount of popular literature. If we instead of just look at what happened over the course of a particular chunk of time, and instead make a plot of how much of the material has decayed over time, we can make a graph like this. This is just a version of a plot that you can also find in the book. This shows if you had a pure amount of material at some starting point, how much of that material will have not transformed as a function of time. So this is just time increasing to the right. At first we have lots, and as time goes on, we have less. So the pink region is how much material is still in its original form. The blue is what fraction of it is now in the form of whatever the transformation is. This is the stuff that has undergone either alpha or beta decay. This is the material, the fraction that has not. Now, I could give this units of years or days or whatever, but what I'm going to measure time in for this is half-lives. Half-life is a unit of time, and it is basically the time that it takes half of the material to transform. So after one half-life, the half of the material is still in its original form, half of it has undergone alpha or beta decay. Now, here is the critical thing. This curve, its shape is determined pretty much entirely by this one parameter. And so we could take that time and say 1 half-life, 2 half-lives, 3 half-lives, and extend it as far as we want. Now you might say, well, okay, what happens as we go from 1 to 2 half-lives? Well, some people naturally think, well, if half decayed in 1 half-life, in 2 half-lives, the rest of it should decay. But in that case, this quantity doesn't quite make sense. You would just say, how long does it take all the material to decay? That's a perfectly reasonable time frame. But what you'll notice here is once half of it is decayed, we have another sample. We have the half of the material that has not decayed. Half of that remaining half decays over the next half-life. So as we go from 1 half-life to 2 half-lives, the fraction of material surviving goes from a half to a quarter, or half of the remaining half. As we go another half-life, half of this remaining quarter will survive, and so there'll be an eighth. Another half-life, a 16th. Another half-life, a 32nd. So the amount of material left gets smaller and smaller, but never entirely goes to zero. And this is the characteristic of unstable nuclei. They follow this trend to the extent that we can tell. And the thing is, this sort of behavior is consistent with this. We could, again, it doesn't matter if this is material that's been sitting around for 1 billion years or was created yesterday, 10% of it decays in a year, or 50% of it decays in some number of years. So about 5, actually. So this sort of thing, the behavior is consistent with this idea that there's a decay constant, that no matter when you look, the fraction that's going to decay in the next little bit of time is constant and predictable. And that number, the half-life or the decay constant, half-life is usually a little more intuitive, is a thing you can measure or estimate based on the decay constant for any number of nuclei. And if you go to various reference sources, including Wikipedia, you will find nice tables of numbers. Some materials have extremely short half-lives. Things like carbon-15 has a half-life of about 2.5 seconds. That's something you could imagine making a bunch of carbon-15 and sitting there and going, okay, how long till half of it's left, half of it's left, half of it's left. That's a quick experiment. The trick is getting enough carbon-15 to make it work. Other things like iodine-131 or cobalt-60 have half-lives from days to years. Again, you could imagine having a sample of this and watching how much decays over some reasonable length of time. Other ones have half-lives of billions of years, like potassium-40. This has a half-life of 1.3 billion years. Now, that's not an experiment you could do. We can't sit here and wait 1 billion years to see how quickly potassium-40 turns in. But we can look for a short period of time and see what fraction decays in that material, calculate, and then extrapolate from that for how much it changes on longer timescales. And in fact, we can check those sorts of calculations using various techniques. So we can measure this for a variety of different nuclei, and the answer varies, but it's always characteristic of the nucleus. Different isotopes of, say, uranium have different half-lives. Different isotopes of carbon have different half-lives. But this is, again, a quantity that seems to just be set by the configuration of protons and neutrons in the nucleus. Now, mathematically, this is a thing you can get your head around. If I asked you, like, how much material is left after some amount of time, you can give me an answer to that. But what I want you to think a bit about, though, is that this behavior is actually kind of weird. Because this fraction of material that has decayed is the fraction of nuclei that have changed from one state to another. And since each of those nuclei is an independent event, why would they as a whole exhibit such regular behavior? Why do they do this? Why does it not matter if I take a bunch of nuclei from all over the world and put them together versus take a very pristine collection, made from some fun nuclear process? They both do this. That's weird. And it's particularly weird it follows this specific trend, where half of the amount goes away every half-life. To understand why that's a bit odd, and this is something I do want to emphasize because I do think it's important, it's useful to look at other systems that exhibit this behavior. One of the ones I like to think about is a tank of water. Say you had a tank of water and there's a valve at the bottom. And at some time, say 0 seconds, you break that valve and it starts to leak. At first, the water's going to leak out quickly because there's a big weight of water pushing things out of the valve. As time goes on, though, the amount of water pushing on the valve goes down, and so the flow gets lower. As the flow gets lower, less material leaks out. And that continues over time. So say maybe in 1 second, half of the material has leaked out. So there's a pretty good flow down there. But at this point, there's less water, so there's less pressure. Turns out, by the way I built this thing, it takes, in the next second, half of the remaining material has leaked out. If in the next second, half of the remaining material has leaked out, and so forth and so on. This is giving something that has a half-life. The amount of water in the tank falls in the same way as nuclear transitions do. And in this case, you can understand why. The rate at which water is coming out depends on how much water is in the tank. When there's lots of water in the tank, the flow is high. When there's little water in the tank, the flow is low. That naturally creates this sort of trend. It's what's called an exponential. And again, this is math that is beyond the scope of this course. But this sort of behavior naturally occurs when the rate of change of something, of some parameter, depends on the value of the parameter itself. In those sorts of cases, half-lives just appear. But why would they appear here? Remember, each nucleus isn't continuously changing from one isotope to another. It's not turning from purely carbon-14 into a mix of carbon and nitrogen. Each nucleus is just one of these and then switches to the other at some discrete point in time. We can see that point in time. We can sit there with a Geiger counter or something and see this electron come flying out. So each one of these events is a discrete event. And they're independent. Like, I could have these nuclei in different rooms. Why would the total fraction of these many independent events follow this particular trend? This is an example of quantum physics. If you want to understand how this transition occurs, what's happening is a change in the distribution of subatomic particles. Just like the configuration of electrons around an atom are described by quantum mechanics, the configuration of protons and neutrons in a nucleus is described by quantum mechanics. It's described in terms of this wave function, which is something that tells you probability distributions, not individual events. That probability, it turns out that in these situations, those probability distributions change in a systematic way over time, in a way that's governed by these same basic equations. There is a process which allows a nucleus to go from being one state, say carbon, into nitrogen. That probability distribution changes over time. And how quickly it transitions depends on whether it's still probable to be a carbon nucleus. So if we look over time, the probability that that any given carbon atom or any has remained that nucleus or has transitioned to another nucleus follows a trend like this. Now, this is a real probability distribution, and each individual particle has some probability to transition. If you have a bunch of these, Most of them are going to make the transition early, about half by the first half-life. But some of them will not transition till the third or the fourth or the fifth half-life. Again, this is just showing that the probability distribution is behaving like a physical thing here. And this is one of those ways that quantum mechanics does things that are kind of counterintuitive. In quantum physics, the thing that defines the probability distribution has physical meaning. The equations that govern how things work describe that. So even though you can't predict how a single nucleus or when a single nucleus will change, a collection of them shows regular behavior. Some carbon-14 nuclei will only last a day. Some will last hundreds of thousands of years. Very few last either of those extremes. Most of them decay around 5,000 years, but on a group of them follows this predictable behavior. So individual events are not predictable, but collections of them are. And again, part of our brain rebels against that. It must be like, if I studied this one nucleus really well, I could say exactly when it decays. Quantum mechanics says, nope. And that can be frustrating to people, but at this point, that's the way the world seems to work. Now, coming back to this observed behavior, what's nice about it is so regular and predictable. This means that we have a good sense of when these sorts of nuclear transitions will occur, which means that these sorts of processes can be used in a variety of applications. For example, things like iodine and cobalt are things with relatively short half-lives, on the order of days to years. These are things that can be hazardous when released to the environment, but also are often used in radiation therapy and in diagnostic imaging. Part of that is possible because if you give someone iodine 131, exactly how long most of that material will take before it decays. Over the course of 8 days, you will have so many number of decays, and another 8 days, you'll have a predictable amount. You can calculate dosages for this. If you have a source of cobalt-60 and it produces so many nuclear decays now, you know that in about 5 years, you will have about half the material left, and then the number of decays will have gone down by a corresponding amount. So if you have an old cobalt-60 source that's maybe 20 years old, you still know how much radiation it's generating, how many of these nuclear reactions are occurring every second or every year or whatever your dosage timescale is. Also means if any of this stuff gets out into the environment, you know how long it's going to be around, which is useful and or scary depending on your point of view. For example, things with short half-life have lots of reactions happening right away, but will be mostly gone in a relatively short period of time. There'll still be some around, but it becomes a smaller and smaller fraction of the original contamination. Things with longer half-lives don't decay as fast, so if you produce 100 atoms of one versus 100 atoms of, say, carbon-15, there won't be as many nuclear transitions, but it'll be around for a longer period of time. And these are things people think about. Now, the other way that this can be useful is that things with long half-lives, like uranium and potassium and carbon-14, these are useful for measuring ages of things. And just to say, I could go on this for days, so I'll control myself. But these things are often used to figure out how old material is. Because if you know the half-life, you know exactly how how many of these atoms were present in the past and how many will be there in the future. Now, you have to do a bit of extra work to turn that into a useful measurement of age, but things that have long half-lives are routinely used to do this. Carbon-14, for example, is often used to date archaeological sites. Things like potassium-40 are able to measure the age of rocks back billions of years. So these are extremely useful things for a variety of fields because they're so predictable. However, there are other reactions, nuclear interactions, nuclear transformations, that are not as predictable, that are equally important. There are nuclear processes that you can make happen faster or slower depending on where you put the nuclei. And these are the two ones you've probably heard about. There are fusion, which is the merging of nuclei, and fission, which is the induced splitting of nuclei. And I want to talk about both of these, okay? So let's first talk about the one that's maybe a little more straightforward demonstration of why certain nuclear reactions only occur in certain environments. That's fusion, putting nuclei together. To see what this is about, let's go back to this picture we talked about earlier, where we pointed out that taking a helium atom, 2 protons, 2 neutrons, and 2 electrons, and pulling it apart into its component pieces resulted in an increase in mass, which means you need to add energy to pull that sort of atom apart. And that most of it goes into pulling the nucleus apart. If you thought about this for a minute, you might go, but wait a minute. That means if I take protons, neutrons, and electrons and assemble them into a helium nucleus, that reduces the mass, that should release energy. That's something that could just happen. Now, you would notice, oh wait, but neutrons are not stable, isolated particles. They tend to turn into protons. But you could still imagine, what if I took 4 hydrogen atoms and tried to stick them together to form a helium nucleus? In the process of that, have a couple of extra nuclear reactions that turn the 2 of the protons back into neutrons. That's actually a process that can happen. And that'll turn out to get rid of 2 of the electrons too. That also results in a decrease in mass. It goes from 4.03 to 4.003. So this process does release energy. Assembling hydrogen atoms into helium releases energy. So why doesn't it just happen? We said nuclear decays result in a mass reduction and so can happen spontaneously. Why doesn't this happen spontaneously? Well, you might say, well, it might be unlikely to take 4 hydrogen atoms and get them into one place. That's not the fundamental problem. We can take hydrogen atoms and assemble them step by step into a helium atom. You would take 2 hydrogen atoms, or just isolated protons, because let's not worry about the electrons at the moment, put them together, make an atom of deuterium, which has 1 proton and 1 neutron. This involves a beta process that throws out a positron and a neutrino. Then you take this atom, which is a proton and a neutron, bring in another proton. This will produce helium-3, 2 protons, 1 neutron. It'll release a photon. It'll release some energy. Then you take 2 of these helium-3 atoms, 2 protons, 1 neutron, slam them together, and you get 2 protons, 2 neutrons, helium-4, and 2 of the other protons fly out. Every single one of these steps results in a reduction in mass, and so releases energy, caught mostly into the motion of these particles. So each one, it is possible to assemble hydrogen into helium in a stepwise way, each step of which releases energy. So again, why doesn't this just happen? The reason this doesn't just happen is because every single particle in this picture has the same electric charge. They're all protons. They're all positively charged. Remember, like charges repel. Like charged protons don't like to get close to each other. They will naturally push each other apart. They don't get close enough to do this reaction. This is still a positively charged object. This is another positively charged object. They don't want to get close enough to do this reaction. This is why the hydrogen in our bodies, because hydrogen is a fairly common element, isn't spontaneously turning to helium. It's just electrostatics. These charged particles don't get close enough for these reactions to occur. And this highlights something important about fusion. Fusion, this change from one nuclear configuration to another, requires the two nuclei to get extremely close to each other. Distances comparable to 10 to the minus 15 meters. If they don't get that close, then nothing happens. You know, if you throw two of these positively charged nuclei at each other, they'll approach, but the electrostatic force gets stronger and stronger, slowing them down until they stop and then fly apart. They don't react in that case because of the fact that that nuclear process, the nuclear interactions that hold nuclei together, are very strong and, you know, contain a lot of energy. They're very strong, but they're very short range. Those sorts of things that allow nuclei to interact and allow beta decay and alpha decay to work only activate when the nuclei are close enough together. So if they don't get close enough together, they'll just fly apart. They won't undergo the reaction and release the energy. You have to throw these things in at high enough speed so that they can, or push them hard enough that they get close enough to each other for those strong forces to take over and convert two nuclei into one. That will result in a release of energy in the form of light or particles or other things. That only works, though, if you can get them close to each other, and their electric charges are going to prevent that unless they're coming together really fast or they're packed together really tight. So you can either put something that pushes those together. That's practically not that useful because practical reasons. The other way to do it is throw them at each other really fast so that they basically don't slow down enough until they're actually touching. Now, we can make this happen on Earth. We can take protons, put them in accelerators, and fling them at each other at high enough speed that they do interact and produce each of these steps. The trick is, to do that, you have to throw the protons really fast. Now, and on Earth, throwing the protons together really fast requires more energy than you get out from the nuclear reactions. Now, ideally, you could use that energy from the nuclear reactions to feed back and power whatever you're doing to throw these protons together and get some sort of, net power out. That is possible. Nobody's figured out how to do it yet. So on Earth, this is not a viable power source yet. It is something a lot of people are working on, but it just doesn't happen naturally because you got to fight the electrostatic repulsion of all of these protons. That doesn't mean it doesn't happen naturally, though, because it does happen naturally. That big ball of hydrogen in our sky called the sun is doing this. the sun is a typical star. It's basically a gigantic ball of hydrogen atoms. And hydrogen atoms, in addition to having charge, have mass. So they have gravity. All of those hydrogen atoms are attracted to all the other hydrogen atoms, so everything is being pulled down towards the center of the star. The center of the star is in a region that's extremely high pressure, so everything's being pushed together, and also high temperature. Everything's flying in really quick. The hydrogen atoms in the middle of the sun are undergoing these reactions. They are assembling into helium, which releases energy. That released energy is in the form of motions of particles and light. This is what is powering the sun, these sorts of nuclear reactions. And we even know that because these nuclear reactions produce exotic particles like neutrinos that we can see. And the amount of neutrinos we see is totally consistent with the rate at which nuclear reactions should be occurring in the center of the sun. So this does happen, and it's not, say, rare. All stars are doing it. It just doesn't happen in environments we're used to. So this one's pretty clearly important. The other kind of process that can happen is fission, where a nucleus splits. Now, in a sense, the thing we called alpha decay is also an example of fission. It's where one nucleus breaks up into two parts, one of them just being a helium atom. Now, this releases energy, which is great. But this has never been a particularly useful thing, or sorry, this is not often practical as a power source. It is in certain cases. The trick is, if you have something that's long-lived, you don't get many of these particles out, so you don't get much energy. If you have something that decays really quick, you can get a fair amount of power, but that power will go away rather quickly. The place where this is often used that I'm familiar with is for spacecraft flying out to the outer solar system. In the outer solar system, there's very little light available, so solar power doesn't really work, and other power sources are tricky. What you do is you use a new isotope that naturally decays at a rate with a half-life of about 100 years. It's usually plutonium-238. Those decays are happening. Each one releases energy. You capture the energy from these alpha particles by letting it heat up some material, and that heat is enough to keep your spacecraft powered for decent amounts of time. It slowly decays away, but it works reasonably well. But this is great for things with limited power requirements. This isn't something that could easily power, like, say, a city. There is a way, though, to mess with these rates. And this is what is called fission. The idea is this thing wants to fall apart. And on its own, in a normal atom, it'll do that at a set rate. But you can mess with that rate a little bit, actually quite a bit. The idea is this. Throw another nucleon into the nucleus. Now, again, you could throw in a proton and do fusion. But as we talked about, if you throw a proton into the nucleus, they're both positively charged. It takes a lot of energy. But what if you had a neutron? Neutrons don't have any charge. They don't mind getting close to the nucleus, and they can get absorbed. Now, if it was one of the most nuclei, it's got an extra neutron. You haven't changed the charge. You haven't changed the way it wants to pull apart. So you just change the isotope of the nucleus, which doesn't do very much. But certain nuclei are not particularly stable. If you add one neutron to them, it starts changing the configuration of protons and neutrons in a nucleus in such a way that the nucleus actually pulls itself apart. into at least 2 fragments. Basically, this is an unstable nucleus, and adding an extra neutron to it basically makes it so unstable it immediately falls apart, breaking into at least 2 pieces. And often when this happens, it doesn't just break into 2 pieces, it breaks into multiple pieces, including more neutrons. Now, if it just broke apart and released energy, that could be useful. You have a neutron source. How you make that is your own problem. And you just bombard these things and they release energy and make various other things. That could work, but what's neat is these processes naturally generate neutrons. So this allows for the thing known as a chain reaction. If you have one of these highly unstable nuclei that react to neutrons in this way, the most famous example is uranium-235. It's a specific type of uranium that does this. If you have a uranium-235 nucleus and a few others nearby, when a neutron comes in, it hits this, that nucleus splits apart and releases more neutrons. And those neutrons can hit other uranium-235 nuclei, which will split apart, producing more neutrons, which will produce more reactions in other nearby uranium-235 nuclei. And this will go on in various ways. Now, the nice thing about this is each one of these steps releases energy. So you could start releasing a lot of energy very quickly. And that's what nuclear weapons do. They just basically let this go on and release a lot of energy quickly. You can also control it by basically, carefully positioning all of your nuclei and making sure your neutrons are properly controlled, and use this to generate a steady amount of power. This is the world of nuclear engineering, and if any of you guys are interested in knowing more about that, I will refer you to the folks at Idaho National Lab who are experts on this. But this is another situation where the rate of the nuclear reactions do depend on environment, and this is how current nuclear reactors work. I will say, just for those of you who are interested, this can happen naturally. There is evidence in something called the Oklo natural nuclear reactor. It was just a place where there was enough of uranium-235 packed into an appropriate region of geology that basically started doing this on its own without anyone there. This is like, I think, 1 billion years old. And it just has all of the output products that you would expect from a controlled nuclear reaction. So this can happen in nature too. It's much less rare than, say, the stars just doing fusion. Anyway, so again, fusion and fission are examples of how nuclear reactions can occur under specific environments, while nuclear decays are things that happen at a more regular, predictable rate. And hopefully I've given you a sense of both the reason why nuclear reactions are so interesting from the point of view of energy, et cetera, but also that these are still examples of places where our intuition starts to have a few issues, like trying to understand why on Earth half-lives exist. Anyway, that's the end of this video, and I'd just like to thank you all for bearing with us through this interesting semester, and hopefully giving you some sense of some of the cool things that happen in physics of electricity, magnetism, and its associated topics. Thank you very much for your time and your attention.